Okay, I think I have fairly covered the Barabasi growth model, various variants of Barabasi growth model, starting from price, Barabasi's deletion, addition, etc., everything, then superlinear, sublinear. But one important problem with all this is what did we try to actually match, or what did we try to actually model? What did we model, or what were the results in the end? The degree distribution. So, at the end we were getting pk, and so what was the inherent assumption? Inherent assumption is that two graphs are same if their degrees are same. So, this was the, although we did not tell it explicitly, but this was the inherent assumption that two graphs are same if their degrees are same. Okay. So, the means we know that this is just a naive assumption, this is not true, that two graphs are not same if their degrees are same. So, there will be some secondary properties also. Okay. So, what we can say that there are secondary properties which does not match, which is the basic inherent problem with Barabasi-Albert model. The first some of the secondary properties which we will say, the number one property which does not match is if we turn to web, okay, we see that there are various bipartite cliques. What are bipartite cliques? So, you have nodes, okay, and every possible connections are there. Okay. I hope you understand. This is means this need not be 4. So, this will be k 4 4. Okay. This will be k 4 4. Am I okay? Okay. So, what happens is you may be remembering the HITS algorithm. Do you remember the HITS algorithm? So, HITS algorithm had two parts. What were the two parts? Means nodes were classified into two categories. What were the two categories? Hubs and authority. Okay. So, what happened is that there was always a bipartite connection between hubs and authorities. Okay. So, authorities actually pointed to hubs, or what is it's the other way around. Okay. So, this bipartite cliques are very common in web. Okay, bipartite cliques are very common in web. So, what happens is all this Barabasi-Albert model or their variants, price model, Dorgovitz model does not really capture this bipartite clique. Okay. When we go on analyzing those evolved graph, we see that bipartite cliques does not exist in those graphs, while in a web, in a normal web, we see bipartite cliques existing. Okay. This is number one. Number two, what we can see is there are many other things, but what we can see is that I think we talked about it, is the clustering coefficient. Okay. So, what is clustering coefficient roughly showing? Yeah, so number of triangles. So, clustering coefficient is is somehow showing the concentration of triangles. Okay, it is roughly showing the concentration of triangles. And what we see, what we have told that in social networks clustering coefficient is pretty high. Okay. While we will see that all these models are really not geared up to produce high clustered or geared up to produce graphs with high clustering coefficient. Okay. So, there are many other points, means what we can think is that, okay, can you give me a formal definition when two graphs can be thought to be similar or same or identical? Huh? Can you tell it in terms of moments? Anybody has done a course on image processing? So, if very statistical, if all the moments are same, then two graphs are same, or two any, it is not a question of graph. If you think two sample data, if all the moments are same, then we say this two sample data is isomorphic. So, what is it? It is degree correlation, degree correlation, degree correlation. So, somehow clustering coefficient is showing a degree correlation. Okay. It is not showing exactly that, but I am telling it is roughly, it is not only 1 degree, it is 3 degrees which are related together. So, really if we want to reproduce a model, or really if we want to produce a model which will exactly replicate the real life, we have to take all these things into consideration. But whereas we have ultimately concentrated on a very simplistic model where we just see the pk, the degree distribution. Okay. Okay. So, fortunately what happens is that although theoretically you have to see this all the moments, it is that if you see the first, second, third moments, all the other moments are really not that effective. Okay. So, you these are not related, but I just want to remind you about that spectral concept. So, you get the first eigenvector, second eigenvector, and what he was showing that each eigenvector has some weight. So, the first eigenvector was able to explain 90% of the entire property, the second the 5%, then it was 1%, 1%, 1% if you remember. So, in conclusion what we can say that in order to map a graph, we have to map all the properties, but perhaps mapping the first, second and third most important property is enough to say that we have almost mapped the graph. Okay. So, now we will concentrate on this bipartite clique, and I may give a, if time permits, I may just give a very brief introduction to clustering coefficient concept. Okay. So, in order to map bipartite clique, you have the vertex copying model. Okay. What is the vertex copying model? The vertex copying model says that when I am a web page, say I am a page which is coming up. Okay. So, I am a page, say I am a page in FactWeb. Okay. So, I am a new faculty who has joined and I am putting off a page in FactWeb. Okay. So, now there will be many links which will be common with other FactWeb links, like department link. In my web page, I will have the department link, the IIT links, okay, something with Shriek, okay, if I have projects. Okay. So, these links will be actually common to any other faculty link. means because faculty link is any other faculty page, because this is a similar category page. Okay. So, what happens? I have some common and some I build independently. Okay. Means this is more relevant if I think of I want to build a review page of complex networks. So, I have built a course page of complex networks. So, what happened is you know the course page. In this course page there are some links to reading which paper should be read. Okay. So, that is mostly copied from some other web pages. Okay. And some is that through my experience I have explored and given some new addition. Okay. So, there are two processes which are going on. One is you are copying from some old pages, okay, and second is you are having some experience. So, this now can be categorized by alpha and 1 minus alpha. Okay. So, alpha is randomly attached and 1 minus alpha is you attach, you take a prototype, okay, you take a prototype and attach it, if the prototype has the ith link and you are putting the ith link. So, exactly put the ith link of the prototype to means exactly copy the ith link of prototype to your page. Okay. So, I go in detail what happens. The detail concept is, so similar to this, you have a web at time t plus 1, one node comes. At each step the same model, at each step one node is appearing and at time t plus 1 node comes. So, node comes with d links, okay, d links. So, d out degree I am thinking it. So, this is again a departure from Barabasi model where you just had it was undirected. But anyway, we have talked about directed graphs in Price model. Okay. So, that part was clear, but here what we are considering is directed with out degree. Okay. So, for each out degree, out edge I say, okay, with prob alpha choose, okay, first is choose a prototype node P say, okay, choose a prototype node P. With probability alpha choose a random vertex and join, okay, no problem. Okay. And with prob 1 minus alpha see the head, okay, I say this is head and this is tail. So, this is P, P has one edge whose tail is here and head is to some other node. Okay. With prob see the head node say V head and attach the head of the out edge to V h. So, what is happening? This is the new edge. So, this the first one got randomly picked to this, the second one gets attached to this. Okay. the third one. So, this has some other here. So, the third one gets attached to this. Probability huh. No, for each h it is independent. The first one with alpha, I toss a coin and I decide whether I will pick randomly or I will follow this prototype. Okay. For if I follow randomly, I pick a random edge and attach. If I follow this prototype, then I see the prototype's ith link and accordingly attach. Huh? Yeah, head node, because I have taken the ith edge of P, every edge has a tail and a head, the tail is always P and head is the corresponding head, and I am attaching to the corresponding head. Okay. So, I think I explained the goal. The goal is that to faithfully represent or the faithfully emulate the how web evolves. Okay. And how can we say that this faithfully emulates the web? If we find that this type of model produces bipartite clicks. Okay. Because in web we see that there are many bipartite clicks, hub authority links. Okay. So, if this type of, so what we are trying to do? We are trying to produce a model which will produce bipartite click. So, this type of model actually will produce bipartite clicks.
So, we will have many head nodes.
Huh?
We will have many head nodes.
B.
Like P has origin of tail.
So, P also has a out degree D's, because everybody is attaching with out degree D.
So, which one of those three connect the new node?
So, this new node also has out degree D. Okay. So, what happens is D alpha means, if you say D alpha are chosen, D alpha edges are chosen randomly and D 1 minus alpha edges are chosen from the subset of P. Okay. Am I clear? Okay. So, this is the model, vertexscopic basic model. Okay. So, now there is a slight variation. So, what happens is, what we say, what is our model till now, that each time step one node is joining, but what we see is that this is not the case, that like you are.
So, why does it give rise to bipartite trees?
No, intuitive, I will tell you the results later, but intuitively what is happening? So, all this, so what is happening? This is also getting connected to this, this is also getting connected to this. So, these nodes are basically slowly forming bipartite clicks. No, they are there. So, it is bipartite click of some size. It is not that every entire network is becoming bipartite click. There are small bipartite clicks existing in the network. That is what happens in the web.
So, for a new incoming node, you choose a new prototype or the same prototype?
No, it will choose a new prototype. Okay. So, what will happen after some time? You will see that some categories of prototype, because see next step, think in the next step what happens if it chooses this and or if it chooses this, both will have same effect. If it chooses this as a prototype or this as a prototype, both will actually have same effect in producing bipartite cliques. Okay. So, as nodes evolves, you will see that category of bipartite cliques or category of nodes representing some bipartite cliques evolves. Okay. Okay, very good. Now, what is the exponential growth model? So, exponential growth model is like that. What is happening is that it is not that this model is very unrealistic, that every time step you are adding one edge, one node. Okay. At every time step you are adding one node. What will happen is that many nodes come out at one time. So, it is happening that you are building a web page and I am building a web page simultaneously. Means simultaneously does not mean exactly at the same time, but at a certain epoch, we can say at a certain epoch. You may be preparing it at 2 o'clock in the night, I prepare it at 10 o'clock in the morning next day, but we can say that it is, and highly unlikely that I will connect to you. Okay. It is highly unlikely that at one epoch one node will basically connect to another node, or one node will have a hyperlink with other node if they are prepared independently. Okay. So now the concept of epoch comes, and if the concept of epoch comes, what happens is that what you say that instead of one node joining at every time step, we can say that some nodes which is the function of the existing number of nodes, joins. Okay. Some nodes which is the function of existing number of nodes join. And what happens is, see, this is very important, is that we see that the number of nodes in the web is increasing exponentially. Okay. Number of nodes in the web is increasing exponentially. So, what happens is, if it is increasing exponentially, then at every time step, at means t number of nodes will begin. So, if at one time step you have k t, the next time step you will have k t plus 1. Okay. So, this is what is happening, that so how many number of nodes are joining at this k t. So, it is a function of k t. So, that is why I wrote it is a function of v t. Okay. If it is exponential, it will be a function of existing nodes. Okay. Added with so I write it more formally. So, v t plus 1 is equal to v t plus f v t comma t. Okay. Second is that added with nodes, edges also come, and edges, it is not only in our model. First model is edges comes only between new nodes and existing node, but at an epoch edges, these edges are more predominant, that if you are building up a new web page, you put more edges, but existing web pages also update and put edges. Okay. So, I write it like this, is equal to E t union So, it is obviously dependent upon new edges which are added, new nodes which are added, but also dependent upon the existing nodes which are there. Okay. Huh? FV is this, GT means is the graph, or I can write VT if you and T. Am I clear? So very formally, if I think a growth can be basically explained by these two factors, one is FV growth of nodes and another is FV growth of edges. Okay. Okay. Huh? FE? Huh. 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 Now we say it is dependent on FV, VT means the existing edges, existing nodes, because there will be some connections between the existing nodes also, and T. And one assumption is the new edges or new nodes which are joining, none will be connected within themselves, because they are joining at the same epoch. KK, am I with you? Okay. Okay. So, now let us try to write. I just write some of the factors. One is I will come with this, that I just say P is equal to growth factor, gamma is self loop. So, I say that at each time step, when a new edge is, when a new node is coming or new web page is coming, you have self loops. So, a web page means, say my web page, it has self loop, go back to home, from each page you say go back to home. So, that is a self loop. So, each web page has some amount of self loops. Okay. So, this is tail copy. Tail copy means how many to existing node and how many to new nodes. Okay. Clear? How many to existing node? Because you have to put the tail, you understand the head. So, what will happen? This is the existing graph, this is the new nodes which are coming, the heads all will go to this existing graph, the tails, some of the tails will come to the new graphs and some of the tails will stay with the existing graph, because these are the edges which are formed in the existing graph and these are the edges which are formed between the existing graphs and the old graphs. That is what we were telling. Okay. Okay. So, and D is out degree. So, let us tell about tail copy once more. So, what is happening? What we did we tell that there are two processes going on. One is addition of node, another is addition of edge, and addition of edge actually can be on FV and also can be on FT, VT. So, what does this FV means? With an existing and new, and this VT means between two existing. Okay. So, that I characterized by a parameter gamma dash, where gamma dash with 1 minus gamma dash I connect between two existing, that is why tail copy. Head will always be. So, what we have told that there cannot be head here. This was our first assumption, that in an epoch nobody will connect to nobody. Okay, means nobody new. Okay. So, head will always be there, tail will be either here or here. So, with probability 1 minus gamma dash, tail will be here, and with probability 1 minus gamma, tail will be in the new node. Okay.
And how many new edges do you create?
Yeah, we come and we have d out degree. Okay. And so, how many, first of all, how many new nodes do we create? That has to be set. So, what happens is f v v t t can follow, say, a binomial distribution, which basically means that v t is 1 plus p to the power t. Okay. So, the p is the growth factor. Okay. So, it is exponential. It is exponential if p is greater than 0, and if it is little greater, means this need not be, do not mix it with probability. Okay. This p can be 5, even then it is exponential, but normally p is a small number. Okay. It is a small number close to 0. Okay. So, it is, even if p is 0.002, you will see an exponential growth. Okay. So, what is v t plus 1 is equal to v t plus 1 minus v t is equal to 1 plus p t plus 1 minus 1 plus p t, which is 1 plus p t common. So, which is, so I write this delta v. Delta v is, this is delta v t plus 1, you agree, is equal to v t 1 plus p minus 1, which is v t into p. Okay. So, now how many edges will be added? What is the out degree given? D. And what, how many self loops are created? Gamma. So, how many out degrees will be added? What are the edges? So, how many number of edges which will be added? V t p into d plus gamma. So, the d is the out degree and gamma is the self. There will be self loops. Okay. Okay, very good. Now, so we know that v t p gamma are all self loops. So, what is left? Left is v t p d. Okay. Its head will be in the existing. Okay. Its head will be in the existing node, no problem. So, now what happens is, so each edge, so how many edges are there still now? At each time, tell me, how many edges are there till now? D plus gamma into V t. This number of edges are existing at t. Means at t plus 1 I am adding, but E t is p plus, because at each step I am actually adding d plus gamma. Okay. So, now what you do is, how many new edges you have to add? V t p d. Okay. So, each edge can be chosen with probability. So, I would say that probability of choosing each edge is same. So, what is my model? Okay, first I should tell my model that how do I choose head? I choose the existing, I choose a existing head. How do I choose this new heads? I choose a existing head and I copy that head to the new head. So, I have I choose this 4 heads perhaps. Okay. I choose this 4 heads, and so the new heads will basically be 1, 2, 3, 4. So, my choice is that I have to choose these heads and I choose these heads uniformly at random. So, each head, how many heads are existing still now? This number of heads are existing, because this number of edges, each edge has a head. So, this number of heads are existing, and how many heads I have to choose then? This number of heads. So, each edge or each head will be chosen with a probability P d d plus comma. Okay.
So what is growth factor actually? P.
Yeah, I showed growth factor P is that at each time step, this is P growth factor. The growth factor is how much it is increasing. So, in a typical wave it will P will be a small values, even if a small value it will go exponentially. So, am I clear that I have chosen the heads? Okay. Accordingly, I have put the heads. So, what is left now? What is left now, Arpit? Tails, choosing the tails. Okay. So, choosing the tails, what we do with I have already told how do you choose. So, with 1 minus gamma dash, okay, I was it does not matter. So, with 1 minus gamma dash you can choose any of the existing nodes at random. So, 1 minus gamma dash into V t. So, how many edges you have? V t p d. So, V t p d into 1 minus gamma dash, this number of tails you choose from existing nodes, and gamma dash V t p d you choose from the new nodes, and which new node? Uniformly at random, because there are many new nodes. Okay. So, which node? Each new node is chosen uniformly at random. So, choice is uniform at random. So, am I clear with the model? Okay. Huh? So, but in many literature also we find that this is considered as gamma dash and this is considered as 1 minus gamma dash. So, it does not matter really. Okay. So, this is the evolving graph model. Okay. So, the next model, so the other model is the Barabasi model, evolving graph. I am just telling the Barabasi model, or you can, in a Barabasi model you have a preferential attachment, instead of that you can have a random attachment. So, that we called uniform linear evolution. Okay. There is another model which is called ACL, its model, which is 3%, Ailio, Chung and Lin. These 3 persons developed this model. And what is this model? This model is very simple. You know configuration model? So, configuration model was what? You create spokes. So, it is the same thing, do the degree distribution, create spokes, and accordingly. So, I am just telling this because I will show you the results for bipartite, that is why I am just showing this. Okay. So, these are 2 reference models, these are not the models which we want to say, but these are the 2 reference models. So, so now first degree distribution. So, in degree distribution what do we see? In degree distribution we see that the linear, both linear and exponential follow power law. With the linears the exponent is actually 2 minus alpha 1 minus alpha. Okay. The exponent of the power law, okay. The power law exponent. Okay. So, it is basically k to the power minus 2 minus alpha 1 minus alpha. So, as long as alpha is small, so you see k to the power 2 minus half 1 minus half, which will be k to the power minus 3. When alpha is half, the degree distribution actually reduces to the Baravasi model. Okay. So, but if alpha becomes 1, then the power law actually breaks down. Okay. It does not stay power law anymore. So, it will basically reduce to the uniform linear evolution model. If alpha becomes 1, it basically reduces to the uniform linear evolution model. Okay. And where you see that follows a exponential distribution e to the power k t. Okay. 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 So, the second part is the existence of bipartite clique. The existence of bipartite. So, what we have in the linear growth model, or we say linear, so k t I d. Okay. So, what is k t I d? Means k I think we know this, k I j means a clique of size, the top is we say top and bottom, so top is of size I while bottom is of size j. Okay, k 3 3. Okay. So, we know k 3 3, accordingly top is of type size I and bottom is of size j. So, k t I d means top is of size I, bottom is of size d and t is the time, okay, because it is always evolving, I say time. So, k t I d, the lower bound of k t I d is basically t e to the power minus I, where I is less than log t. So, yeah, k t I d is a clique, means clique of size I and d at time t.
The number of clicks. The KTID equal to the lower bound of.
Yeah, number of clicks. So, this is number of clicks. So, what you see that I is less than log t means this. So, let us put I is equal to log t to the power minus half. Okay, t to the power half. Yeah, time, because it is a evolving graph. So, what we have is gamma t to the power minus half. So, gamma t to the power minus half. E to the power log t to the power half is T to the power half, sorry. So, what is happening is it grows sublinearly, but it grows with T. The bipartite network grows sublinearly, but it grows with T. Click. Okay. So, what would happen? Tell me, when can I say that no clicks are growing, are there, or clicks are yeah, and when can it be? When it will become constant, okay, independent of time it becomes constant. If it grows linearly with T, then you say that it is growing and number of bipartite clicks are enough, but if it becomes constant, then we say that it does not exist. So, now this exponential growth model, Varun, you have anything to say? Exponential growth model, you find that when you take k t I comma I, it is its lower bound is 1 plus p to the power c t, where c is less than 1 and I is less than 1, theta is less than 1 and theta is less than 1, sorry. So, let us see this. So, what happens? It is 1 plus p means it is growing exponentially, but not as fast as the network is growing. Network is growing at 1 plus p to the power t, but it is growing to proportion to the network, it is growing even exponentially. And what does this show? This is a factor less than 1, okay. This is a factor less than 1. This is a factor less than 1. Okay. So, what is happening is, as I becomes big, this becomes small. So, what is happening? As the size of the bipartite click increases, we see that number of bipartite clicks decrease. Okay. Even then we can, there will be a crossover point, even then we can show, we can see that even for large I, there it will follow, it will be proportional to, or it will be proportional to some t. Okay. It may be sublinear something, but it will proportional to some. Whereas, if I take the uniform graph model, we see that k for I greater than something like e square by e square plus 2, e square plus 1 is nothing, it is 10, okay, around 10. So, t I okay. So, you see that it is less than 2, and for ACL model we find that KII, in ACL model there is nothing called time, because ACL you have, it is a basically configuration model. So, you see that it is constant if I is greater than 2 beta minus 2. Beta is what we say Pk is equal to k to the power minus beta, okay, this beta exponent, power law exponent. So, I think we have covered enough of growth models, both the degree distribution, the second order properties, and next class we will study small world.